the answer, I'll be checking what is the probability, which means that the area between the measurement that you have for x, between what is the probability that your measurement between -2 to +2. So once you run the Python code, you will need to modify this Python code to find the area between -2 to +2. So that will give you probability that -2 less than x less than 2. So this is what I need. And the other values that I need is the following. So what is the probability of the corresponding mapped measurement y equals x plus b, which is basically the distribution is as such. So I will need you to give me the probability of the mapped measurement between 2 to 4, which means that you will need to find the area between these range. So that will give you probability that measurements takes mapped measurement y takes values between 2 to 4. So what is this probability? Okay. So I will be checking this two probabilities. So these are the two extra things that you will need to do. So I'm going to pass on to this sign sheet. Please make sure to sign that you implemented and you submit it. All right. So today I am going to start from the packet switch example of chapter number 5. So this packet switch example will serve as a basis for many examples to come. Just to recap, so this packet switch example, the problem description is as follows. It has 2 input ports and it has 2 output ports. A packet can arise in any of these input ports. So probability that a packet arrives in one of these input ports is 1/2. Therefore, no packet arrives in one of these input ports is also 1 minus 1/2 equals 1. Okay. So that's what it's written. No packet, probability that no packet arrives in one of these input ports is 1/2. Now, when packet arrives with probability 1/2, that packet has equal chance to go to any of these output ports. So that packet, if the packet arrives in input port 1, that packet can go to output port 1 with probability, because it comes with probability 50%, 1/2, and it goes to any of these input ports with probability 1/2. So and operation here. So it's an intersection. So probability that the packet goes all the way to output port 1 will give is 1/4, or a packet can arrive in any of these input ports, can go to output port 2 with probability 1/4. We have 2 random variables. We are dealing with 2 random variables from now. So random variable x represents the number of packets arrive in output port number 1 and variable y represents number of packets arrived or destined for output port number 2. So when you see no packet arrives in any of these input ports, so therefore no packet will be in any of these output ports, that contributes x equals 0, and here y equals 0. When packet arrives in output port number 1, which means that this contributes 1, 0, which means that x equals 1, comma, y equals 0. Similarly, packet to output port number 2 contributes to 0, 1, which means that x equals 0, comma, y equals 0. So, packet can arrive in input port number 1. At the same time, packet can arrive input port number 2. So, now these two packets can arrive in two different ports, but these two packets can go to output port number 1. So, in that case, your x is going to be 2 and y is going to be 0. Similarly, packet can arrive in any of these input ports simultaneously, but can go, both of them can go to output port number 2. So that way, your contribution is going to be x equals 0, y equals 2. Okay. Now, packets can arrive in both of these input ports, but one packet can go to output port number 1, and another packet can go to output port number 2. So in that case, the contribution is going to be x equals 1, y equals 2. Okay. Now, the total number of the constraint here is that the total number of packets in the output port cannot be more than 2. Is that crystal clear? The total number of packets arrived in output port number 2 cannot be more than 2, which means that the random variable x, the constraint here is that random variable x plus random variable y has to be less than or equal. So that is the reason the impossible outcome is, so this is an impossible outcome because here x equals 1, y equals 2. So x plus 1 becomes 0, so that is not going to happen. Similarly, this point and this point, these 3 points are impossible outcomes. So therefore, the random variables do not count. So in our last class, actually, we did go through this entire example. We found the joint range. So we found the joint range, and joint range I wrote it down right from here. So joint range was S sub x comma y equals, anybody remembers? Joint range was 0, 0, 0, comma 0, 1, comma 0, 2, comma 0, then 0, comma 1, 0, comma 2, and then 1, comma 0. That was the joint range. The mapping, we also went through the mapping, this mapping, we found the outcomes here. N, comma n is one outcome. No packet arrives in input port number 1, no packet arrives in input port number 2, no packet arrives in input port number 1. One packet arrived in input port number 2, but that went to output port number 1. So this A subscript 1 means that it went to output port number 1. So make sure, please, you don't get confused. Okay? So this A1 does not mean that it is in input port number 1. So this second argument means that it is input port number 2, but this A1 is, I'm denoting A1 to represent that packet arrived in input port number 2, but it went to output port number 1. So similarly, this is the conversion. And for each of these outcome, I mentioned the probability here. So this is the probability. So we have this outcome zeta, and this is the probability. This is the probability. Okay, and then we found the joint PMF. So because we are working with two random variables, we did find the joint PMF. So the joint PMF of random variable x, comma y, taking values x equals 0, y equals 0. So by definition, joint PMF of random variable x, comma y, taking value 0, comma 0 means that probability that random variable x equals 0 by definition and random variable y equals 0. Okay? So this is basically a probability of the elementary outcome, which is n comma n, and this probability is 1/4. Okay? And this comma means it's an AND operation, intersection, so that's why probability that no packet arrives in input port number 1 is 1/2, and probability that no packet arrives in input port number 2 is 1/2. So 1/2 times 1/2 becomes 1/4. Okay? Now, previously we went through the formula in case you have multiple outcomes. Multiple outcomes, so which means that here, so probability that, what is the probability that any of these outcomes can happen? So we can see that this part and this part, n comma a1 gives you probability 1/8, and a1 comma n gives you probability 1/8. Okay, so I was guessing that you will ask me this question. That, okay, so here this comma represents and, which becomes 1/2 times 1/2 is 1/4. How about this comma? So this comma does not represent and, it is basically or, so that's why you are getting this plus operation. Why? Is because this probability of this set means that, okay, so just to go back to chapter 2. Okay, so when we have the outcome, sample space equals, let's say sample space of a dice is 1, 2, fair dice is 1, 2, 3, 4, 5, 6. Okay, and one event is, let's say 2, 4. This is an event. Okay, what is the probability of this event? I know that probability of elementary event, which is 1, equals probability of elementary event 2, and so on, all the way equals probability that elementary event 6. Just to reiterate, it is 1/6. Okay? Because we have two elements here, so what we do, this probability is going to be probability of the elementary event 2 plus probability of the elementary event 4. It's very confusing. So here you see that it is 1/6 plus 1/6 is going to be 1/3. Okay? So this is the exactly same principle that I applied right here. So it is basically a set of two outcomes. So that is the reason you get the addition. You see the addition. So I went through the 3D plot. I went through this 3D plot. I went through the tabular format as well. So I am going to go through the next topic. Okay. So we are going to find the marginal probability mass function. So the marginal probability mass function marginal probability mass function of random variable we denote it with x, taking value x, which is basically by definition probability that x equals x. Why I call it marginal probability mass function? Because we are going to find this probability mass function of a single variable from the joint probability mass function. So from the joint probability mass function, we are trying to find the probability mass function of one of the random variables, marginal probability mass function of random variable x, and we are going to find the marginal probability mass function of random variable y. Because we are dealing with discrete random variables. So from the previous example, we dealt with discrete random variables. Then let's talk about discrete random variables first. So by definition, marginal probability mass function of random variable is taking value xj, where xj, these are discrete values. So by definition, it is probability that x takes value exactly xj, which we are going to try to find it from the joint probability, which is probability that x equals j and y could be anything. And I have one example in any more. So in other words, you have probability that x equals j, y equals y1, union, or union, x equals xj, y equals y2, union, dotted, y could be anything. That's all. So you just keep xj fixed, and you vary y. So therefore, you can write it in the form of summation as such, because these are odd, so you can write it in the form of summation, and this is basically a joint PMF. So given the joint PMF, you will be able to find the marginal PMF of a single random variable. Similarly, we are dealing with just two random variables. In case we deal with n random variables, it's basically extending to n marginal probability mass function of one of n random variables. Similarly, the marginal PMF of y is basically you just vary. So actually, yes, it is correct. So marginal probability mass function of y taking value yk. So you keep yk fixed and x can vary anything. So in that case, your summation index for the previous case it was k, and here summation index is j. Now these formulas will be clearer right from here. Again, I adapted it from example 5.7 of the textbook. Adapted means I did modify the example a little bit so that I can link it with the previous example. Again, we are starting with packet switch example. A packet switch has two ports with two input ports and two output ports. At a given time slot, a packet arrives at each input port with probability 1/2 and is equally likely to be destined to output port number 1. Let x and y be the number of packets destined for output ports 1 and 2 respectively. Find the marginal PMF of output ports. That's represented by random variable x and y. Okay? So for this example, you will need to solve solution. Because it involves two random variables, you will need to find the joint PMF first. First, find the joint PMF. First, you find the joint PMF. So joint PMF, we denote it with joint PMF of random variable x, y taking value x, y, which is basically probability that random variable x equals x, comma, random variable y equals. Y. Okay. But how to get that? How to determine the joint PMF? So to find the joint PMF, start with, because we are dealing with random variables, start with joint range. Joint range. So joint range, we denote it with S sub x comma y. Is basically, what was the joint range? You remember this? 0, 0, 0, 1, 0, 2, 1, 1, or we finished 0. So 1, 0, 2, 0, and then 1, 1. So this is basically joint range. 1, 2, 3, 4, 5, 6, 8. This is basically the joint range. So again, this number represents the number of packets destined to output or arrived in output port number 1. So x, and this number represents the number of packets arrived or destined for output port number 2. So this is the joint range. So in other words, we can write, in short, we can write x comma j, x sub j, y sub k, as such, and then we say that j equals 1, 2, 3, k equals 1, 2, 3. So joint PMF in tabular format, tabular form. So your joint PMF of random variable x comma y taking variable x, y. So here you have j this way, and let's put k that way. So you have x1, so 1, 2, 3. This corresponds to x1, x2, x3. So this is indices, and actual packets are, when x1 would be 0, actual packet x1 equals 0 here, x2 equals 1 here, and x3 equals 2 here. So k is 1, 2, 3. So yk, y1 equals 0 here, y2 equals 1, and y3 equals 2. So don't get confused with the subscript y1, y2, y3, because y1, y2, y3, their values are different here. So the value of y1 is 0, value of y2 is 1, value of y3 is 1. We did find the joint PMF when x1 equals 0, y1 equals 0. What was the joint PMF? you remember? What was the joint PMF when x1 equals 0, y1 equals 0? We went through this in our last class. It was 1/4, right? 1/4. And when x2 equals 1, y1 equals 0, so 1, 0, it was 1/4. And this one, when y1 equals 0, x3 equals 2, it was 1/60. 1/60. And then here it was when x equals number of packets destined for output port number 1, 0, number of packets destined for output port number 2 was 1. How was that? It was 1/4. And then here it was 1/60, right? Yep. 1/60, here it had 1. So can you sum them up, guys? 1/16 is 1/8. 1/8 plus 1/8 is 1/4, and 4/1/4 is going to be 1. So sum of all the joint PMFs should be 1. Otherwise, it's not joint PMF. Make sure, guys. So when you determine the joint PMF, sum of all the joint PMF should be 1. That's the only way to check that the screen is clear. Okay, so that's the joint PMF. Now the other values, when you see empty, these are impossible events, so therefore there will be 0. Now this problem is asking you to find the marginal PMF of random variable x and y. So to find the marginal PMF, you will need to find the joint PMF first. So I'm going to directly use this formula. Okay? I'm going to directly use this formula. So marginal PMF of random variable x, it is marginal PMF of random variable x taking value x1, which is by definition that probability that random variable x takes value exactly x1, because the experiment we have consists of involves joint PMF, so we are going to write it in the form of joint PMF. So probability that x equals x1, comma, y equals n. N. So which is basically probability that you keep x equals x1 fixed, comma, you can have y equals y1, union x equals x1, comma, y equals y2, union you have x equals x1, comma, y equals y2. That's all you can get. So now each of these is basically a joint PMF. So it's basically, you can write, because these are odd, you can write probability that x equals x1, comma, y equals y1, plus probability that x equals x1, comma, y equals y2, plus probability that x equals x1, comma, y equals y2. So by definition, this is your joint PMF of random variable x, comma, y taking value x1, comma, y1. And by definition, this gives you joint PMF of random variable x comma y taking value x1 comma y2, and by definition this gives you joint PMF of random variable x comma y taking value x1 comma y2. So again we have keep writing. So it is, in other words, you can directly write k equals 1 to 3 joint PMF of random variable x comma y taking value x1. So this x1 and this x1, same x1, comma you have yk. You can write it directly in the form of summation. But because I expanded it nicely so that for us to understand easily, so it is basically joint PMF of random variable x comma y taking value x1. I'm going to start with, let's say, so I'm going to start with marginal PMF of random variable x taking value 0, which means that x1 equals 0. So therefore, it is going to be joint PMF of random variable x comma y taking value 0, comma y1 starts with 0, plus joint PMF of random variable x comma y taking value 0, y could be 1. X equals 0, y could be 1, plus joint PMF of random variable x comma y taking value 0, comma 2. So now we know these values. These values, joint PMF of random variable x comma y taking value 0, 0, we know it from the joint PMF. It is 1. So, it is 1/4 plus 1/4 plus 1/16. How much is it, guys? It's 9/16, right? Yes, it's 9/16. Similarly, marginal PMF of random variable x taking value 1, which means that it is joint PMF of random variable x comma y taking value 1, 0 plus joint PMF of random variable x comma y taking value 1, 1 plus joint PMF of random variable x comma y taking value 1, 2. Can we have 2? No, this is 0 basically. This will be because 1, 2 does not exist. So this probability is 0. This is an impossibility. So it is going to be 1, 0 is 1/4 plus 1, 1. How much was it? 1, 1 was 1/8. 1/8, which is 3/8. And marginal PMF of random variable x taking value 2 is going to be joint PMF of random variable x comma y taking value 2, y could be 0, but y cannot be 1, 2, any of these. X equals 0, y equals 1, does not exist. So it is basically 1/16. Now you add them together, check. 9/16 plus 1/16 plus 3/8. This should be 1, yes. 9/16, so this is 10/16, and you multiply 2 numerator, denominator 6/16, so 6, this is 1. So that's your marginal PMF of random variable X. In compact form, this is what I want. In compact form, mathematically, so marginal PMF of random variable X comma X taking value X, which is by definition probability that X equals X, which is from joint PMF probability that X equals X, Y equals anything, you write it in the form of case. So which means that it is 9/16 when X equals 0, it is 3/8 when X equals 1, and it is 1/16 when X equals 2, and here Y is anything. Okay. So this should be that answer. Now find the marginal PMF. Now pursue similar procedure to find marginal PMF of Y, which is basically PMF of random variable Y taking value Y is going to be, you just write this probability and make sure that you add them together to, you sum them up, make sure that they, that summation is 1. So that's all you do, and I'm going to put this part as part of the homework. I'm not going to go through this part of homework. So you just follow similar procedure. All right. Next example. This example is relatively easier, but it's confusing a little. Okay. In this example, it's about joint PMF as well. Here you have two, you have two die loaded. Okay, an experiment consists of tossing two loaded dice and noting the pair of numbers X, Y facing up. Guys, a die has 6 faces, right? Each face has number of dots. For example, one face has 1, like 6 faces, has 6 dots. Okay. What you have when you toss a die, the reason we are saying that here loaded is because still fair die, but the order matters. So the way I hold the 2 dice, so 2 dice, the way I hold, this order matters. I cannot interchange. Okay, so position of 2 dice, they remain intact. So these positions are basically represented by J and actually the number of dots is represented by J and K. Now these two positions, so the first argument is first die and the second argument is second die. So number of dots for the first die is represented by X, number of dots represented by number of dots facing up represented by the second argument, which is Y. Okay. The main confusing part is that you see two dies you have, so therefore you are supposed to have 36 total life. But here it does not give you 36. The probability of two die, when you multiply them, it does not give you one probability, one outcome, 236. It's because of this order. Okay. Now, let's say I have this first die, this is second die. Okay. All what I care is look at the number of dots facing up. Now, let's say first die gives 2, number of dots 2, second die gives number of dots 1. So then outcome is going to be 2 and 1. So first die gives number of dots facing up 2 and second die gives number of dots facing up 1. So the outcome is right here. So this probability is 1 over 42. Now I'm giving you in a moment why it is 42, why not 36? Because 6 times 6 is 36. Okay. Now, again, the first die can give the number of dots facing up 1 and second die can give number of dots facing up 2. So in that case, 1, 2 will give you 1 over 42. Again, I'll talk about why it is 42 in a moment. Okay. Now, order matters, guys. Order matters. I reiterate again and again. Order matters. Now, first die gives number of dots facing up 2. Second die gives number of dots facing up 2. Okay. So you record 2, 2. But again, what you do, because you just care about the number of dots, in case you interchange these two die, still you can see this number of dots facing up 2, 2. That can happen. So because 1, 2, 2, 1 gives you two different outcomes, that using same principle, 2, 2, and you just flip 2, 2, is giving you two outcomes. So that is the reason you are having these joint range as follows. I'm going to use different colors. So you may want to write down this joint range because of the loaded die. So joint range S sub x comma y is going to be, one outcome could be 1 comma 1, 1 comma 2, 1 comma 3, dotted, 1 comma 6, and because you just care about the number of dots, therefore you can have another 1 comma 1. Similarly, you have 2 comma 1, 2 comma 2, 2 comma 3, dotted, 2 comma 6, and then you have one repeated entry, 2 comma 2. And so all the way, 6 comma 1, 6 comma 2, 6 comma 3, dotted, 6 comma 6, and you will have another 6 comma 6. And you will see x comma y equals, you will see how many elements here, 1, 2, 3, 4, 5, 6 here, 6 times 6 is 36, and you have this 6 additional entry, and that is the reason you have total 42. Total 42 elements. Total 42 elements, and that is the reason for each outcome your probability here is 1/42. Except for outcome 1, 1, 2, 2, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. You have two same outcomes, that's why you have 2/42. Okay? So here is the joint here. This is your joint here. This is your joint here. Only thing, it's easy, but only thing that is changing the entire philosophy is this word loaded. Because of this loaded, instead of 36, you have 43. Now find the probability that the minimum number of dots facing up is 3 is going to be, something is going to finish in, is going to be the addition of you just add all these values to find the probability of the minimum number of dots facing up is 3. And then find the marginal PMF. Marginal PMF is basically, so you just have to find. Let me go through that in our next class. This marginal PMF I need to do this example. Okay? All right, so I'm going to stop right here, and then I need 2 more classes to finish chapter 5. And then when is our next exam? 17th, right? I'm just going to give you a review right before. Okay, thank you guys. Have a nice weekend. I will see you on Monday.